And we've created our own example workbook. So this is a whole bunch of examples that will give you guidance and the knowledge to develop your skills in order to do the homework assignments, right, and to do your tests, obviously. So every unit is going to have its own little examples book. This first one is transformations of functions, which is what we're doing. This gives a ton of information too about what you're learning in math. It gives, the first page obviously is the unit lessons that we're going to be doing, so 5 lessons. And just about homework, it says most days you'll be assigned some pages to read in the student guidebook, the one that you're going to get shortly, or you have the first chapter. So I might assign you like a little bit of reading to do before a day's class. You'll come to school, we'll work through some examples, and then you'll get time to practice your skills daily in class by doing assignments and little maybe hand-in assignments. Like I said before, I'll try and give as many hand-in assignments as I can to you, because they're not going to be counted for marks, right? But so it's just for feedback. These are taken right out of the Department of Education curriculum, just so you know exactly what the department says you have to know for grade 12 pre-cal regarding transformations. It's very technical, but that's how the Department of Education publishes things. So if you're ever not sure what you're doing, obviously you can jump on the Manitoba Education website, but we've reproduced them here. So it just says describe the effects of horizontal and vertical translations, horizontal and vertical compressions and stretches. You'll also be doing reflections and inverses of graphing. Now, many people think this is the toughest unit. So if you can get through this one, if you don't like graphing, I think most of the course will kind of be a little easier after this one, but it's just getting back into the graphing and relating graphs and equations. So here's some key terms and vocabulary, and I thought I might actually give you the vocabulary, a little bit of the vocabulary today, so maybe we can kind of preload you. So I said that I want you to have a basic knowledge of those 4 parent graphs so far, right? The linear, the quadratic, absolute value, radical. We are learning some new graphs in this course, but sometimes you're not going to be given a true parent graph. It'll be a function, but it won't really be a graph that we know the equation of. A lot of your work comes like that. So if you just kind of flip over, for example, on page 5, the very first graph you're given, this is not a graph that any of you really recognize, is it? It's kind of like 2 absolute value graphs, one flipped and put together. This is common in the grade 12 pre-cal course. They just give you a function. Is that a function, by the way? Yep, it passes the vertical line test. It's actually, it would be a piecewise function, right? It's only part of a line, positive line, part of another, negative, linear, and then another positive. So part of your job, it's not to come up with the equation of this line. So relax right there, you don't have to the equation. When it's not one of our parent graphs, we're just going to refer to it as an f of x graph. Okay, so you don't have to come up with the equation, but you have to be able to do transformations on it. So what do I mean by that? Well, these are the transformations you're responsible for. A translation means, this means the graph is vertically shifted up or down, or horizontally shifted left or right, or both. We've already seen that with quadratics, right? We had the quadratic. You guys already showed me, you knew what that was all about. When I said, can you tell me what the difference is between this graph and this one? You said, okay, that one's just that one shifted up 3. So a vertical shift up or down doesn't change the shape at all. A translation doesn't do any shape changing. It just moves the whole graph up or down, left for you guys, or right. Okay? Now a stretch and a compression, they actually are the same they're in the same family. A stretch, obviously, stretches the graph vertically, right? Vertically or horizontally. Makes the graph wider, right? Means the graph is stretched vertically. And if it's stretched vertically, we usually say that. We say stretched vertically. What the graph is becomes taller, right? That's what will become. Or stretched horizontally. And that would mean the graph, even if I had a parabola like this, if I stretched it horizontally, it would become wider, right? Compressed. Compressed means squashed, right? Either squashed vertically or squashed horizontally, okay? This means, this means, okay, I'll try and print, means the graph is compressed vertically, becomes shorter, or horizontally, and I'll put the notes on the website too, on the blog, becomes narrower. Okay? I'm going to leave inverses today, but I'll talk about reflections. Means the graph is reflected over there are sort of 3 reflections, but over the y-axis. So that means the graph just flips over, like mirror image, over the y-axis, okay? This is actually, if it's flipped over the y-axis, an interesting thing happens. Like, for example, let's just take this. Let's say my graph only consists of, maybe my graph is only the point, let's say my graph is the point 4, 5. That's it. My function is just one dot, one coordinate point. Passes the vertical line test. It's not a big function, but there it is. Let's say I say it's reflected over the y-axis. Okay? What happens to that point if it's reflected over the y-axis? Can you kind of guess what the coordinates would be? What would change?
The size.
So what would the coordinates of the new point be? 4, 5, right? So it's kind of interesting. If there's a reflection over the y-axis, all the x values become their opposite, right? So our graph is reflected over the y-axis. All the x coordinates become their opposite. Oops. Meaning, let's say I had a point, let's say my point was, -6, -9. Reflected over the y-axis, the x changes value, but the y doesn't, right? So reflections over the y-axis, just the x value changes. Of course, you probably know what's coming. It can be reflected over the x-axis too. So when I have a graph reflected over the x value, or the x-axis, the y values, the y coordinates become their opposite value. They're opposite in value. It's still the same distance away, right? Like -4 and 4 are 4 units away from the y-axis. Still the same distance, but just the value changed. Okay, there's one more reflection. Anyone know the third type of reflection? There's kind of a third axis sort of hidden. I kind of mentioned it before. Yeah, the diagonal, right? Because our axes, our x and y axes, those are the main axes of the Cartesian plane, right? X and y. But this guy is a really important line too. Remember what he's called? It's the y equals x line. Okay? Or reflected in the y equals x line. Guess what happens there? If there's a reflection in this line, it's kind of harder to do, and that's why we'll save this. That's what the inverse is. What happens, can anyone sort of think about what would happen to the coordinates? Something interesting happens if they're reflected in this line. What do you mean by that? Can you give me an example? Someone else had something over here. Who was it? It was over in this corner. This is kind of, I think you've got it, Evie, but I couldn't really hear you. The x and the y switch values. They just switch. That's kind of fun, actually, right? So in the x, so if I had, it's kind of hard for, okay? So I gotta draw my line in though. So here's this perfect y equals x line. So if they are reflected in the x equals y line, let's just say I had this point 2, 7. You know what the point reflected here would be? 7, 2. It's harder to visualize, I think, because we're so used to the x, y. We'll get to there. But that's going in, that's what we're going to be studying. And it's a lot easier than I think you might think it's going to be. So we're going to switch over, and we're just going to, before class ends, because by the way, class ends at 2:10, or probably 2:05. All of our classes have kind of changed a little bit by 5-10 minutes here and there, so I'm just getting used to the new times as well. So I want to introduce this topic to you, and you can finish your homework that I assigned to you if you haven't done that already. But we're just going to talk about horizontal and vertical translations. So you can see the textbook you're going to get is great, right? And all the examples are done for you in the textbook. Remember I said cover up the answers, don't look at the answers when we were doing them? But it's great to have examples that are done for you in the book, because then you can kind of look at home and make sure that you know what's going on. But it's also really important not to have all the examples done, and that's what we're going to do in this book. These are examples we do together, so we're kind of creating our own knowledge here. And hopefully, again, anytime you have a question, just ask me or pipe up with a comment. So we're going to talk about horizontal and vertical translations. The first things we do is we're just going to do some graphs that you don't even recognize to kind of put your mind at ease too. You don't have to have this super duper knowledge of all your parent graphs right now, because we're just taking a generic graph that everyone here is seeing for the first time. So because it's a generic graph, I don't have the equation for it, and we're just going to call it f of x. So that's another thing you have to get used to. If I just say we're studying f of x, that means we're just studying a generic graph, and we're studying it in that function notation form. So that makes a bit of a difference too when we show our answers. So for a function, for any generic function f of x, a vertical translation is shown by, okay, I'll show this way first. Y equals f of x plus k. If there's a value attached to the k or to the function at the end, that's indicating a vertical translation, right? Just like that plus 3. Agreed? So this is my f of x, my equation. Here I know what my equation is, right? And I just attach the 3 to the end. If there's a number attached to the end of the equation, telling you translate the graph vertically. Now, it's usually written as f of x plus k, but notice I could also push the k over to the left-hand side. If I push the k to the left-hand side, it becomes a negative. Some textbooks have like putting the k on the left-hand side because it actually affects the y value, but either one of these forms is fine. But you can see it's outside of the function altogether, right? So what does a horizontal translation look like? Because that was vertical. A k value is telling you the graph is going to be either shifted up or shifted down. A horizontal translation is defined by if there's a number attached with the x, inside brackets with the x, like actually inside the function, that tells you how many units to move the graph either left or right. Again, if I take it back to the grade 11 course, what if I gave you this? Y equals x plus 3 all squared. Okay? This is a shift up for you, right? What did this do? What kind of parabola was this?
Shift to the left.
Yeah, shift to the left 3. Okay? So see, anything inside, any number attached to the x inside the function, inside brackets, underneath the square root sign, if it's attached to the x, it's a horizontal movement. If it's outside the x, if it can be moved over to be with y, it's a vertical move. Okay? So, it says, our first example, here is the graph of y equals g of x. Okay? So this is g of x. It's just a generic graph. You don't know what the equation is, so we just have to use it in generic form. For each of the translations given, sketch the image graph after the translation, write the equation of the image graph, and then state the domain and range of each function. Okay. They want us to do, it says write the equation in terms of, I think, let's do them separately. I'm going to do separate graphs. Okay, what would a translation of 4 units left look like? Okay, this is pretty easy, right? I have 4 critical points, agreed? By critical points, I mean kind of the corners, right? The vertices. Those would be my identifiers. If I can just translate those, I could easily move my graph to the left as well, right? So how would you approach this? If I said to you, I want you to draw the new graph, and I want you to draw the graph of the translation 4 units left, what would you do? If I didn't give you any other instructions.
You have to take from the point and you have to move 4 units.
Yeah, would you just take these kind of just manually and redraw them? Okay, 1, 2, 3, 4. And I'm just using my critical points, right? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I mean, it's pretty obvious in this picture because it's so straightforward. But notice I started left to right, and that's how I moved my points. And that's what I'm going to suggest you to, because sometimes the graphs are going to get more convoluted and you're going to lose track of what dots to connect first. But I draw them in the order, or I list them always in the order that I'm going to connect. Okay? I'm going to do these as 2 separate graphs and not as one graph, right? So I'm going to do this, and let's call this one, I can't use G anymore because G was already used for this graph. So let's call this one, or actually we'll still use G. Sorry about that. How would I write the equation of this new graph that I've, because it can't just be called g of x. It's g of x with a shift to the left, right? So it would be y equals g
X plus 1.
Agreed? That's how I would write it. Now I have to leave it in this generic form because they didn't give me the actual equation, right? If I actually had the equation, like an x squared equation or an x cubed, then I could write it in a more proper form, but because they gave it to me in generic form, I have to leave it generic form. Everyone agree? That shows a shift 4 left, agreed? Okay, let's do this one, and I'll actually record it here too. This is y equals gx plus 4. Okay, what would a translation 1 unit up be? I'm going to do it in a different color. I'm going to use red for this one. If I was just going to do 1 unit up, it would just be, this might even be easier, right? 1, 1, 1, 1. So again, we're starting off pretty easy here. It will get a little more difficult in days to follow when we start combining our transformations, right? We're going to be doing transformations with shifts and stretches and reflections. That's when it gets a bit tougher. Okay, so what would the equation of this one be? If I was going to show, here's my, this is all they gave me, kind of in that generic functional notation. So how would I show a shift 1 up here? What would my equation be?
G of x plus 1.
Yeah, g of x plus 1. Okay? Now, I am going to introduce, no, maybe I won't. Never mind. I'll save that. There is a way to do that if you've taken this course before that involves like mapping, taking the critical points. How many people have done mapping before? Does that make sense to you, mapping? I'll save that for a slightly tougher one, okay? Let's try a couple more examples, okay? And then I will let you go for the day. Okay, everyone fine with this kind of notation? Let's move over here. Example 2. Here's the graph of y equal j of x, right? It can be any letter of the alphabet. Sketch the image graph after translation of 4 units right and 5 units down. Write the equation of the image graph in terms of the function j. State the domain and range. Oh, sorry, I knew I forgot something. We were supposed to do the domain and range too, right? So let's do the domain and range. Okay. Y equals g of x. We'll do the domain and the range. Then we have to do y equals g of x plus 4. Domain and range, and we have to do y equals gx plus 1. I forgot to do that. Okay, g of x. What's the domain of just the original graph? The furthest left, the graph goes as -1. The furthest right is to 6. So I'm going to use symbol notation. -1 comma 6 square brackets, right? And what's the range of the original graph? The lowest the graph goes is 1, and the highest 6. Okay, what about the gx plus 4, the horizontal translation? The domain changes, right? It shifts to the left. So it's from -5 to +2. And the range is from, what's the range? Why didn't the range change? Yeah, there was no vertical change, right? So I could look here, now that I know what I'm looking for, I could clearly look here and say, oh, that's just a horizontal shift. The range won't change at all. Same with this one. The range is going to change, but the graph hasn't shifted horizontally. So the domain should stay the same. And sure enough, the domain is the same, right? The black and the red domain is the same. So -1 to 6. And the range has been shifted up 1, so now it's from 2 to 7. Okay? All right. Here is the graph of j of x, except it says f, so I'm going to change that to j. j of x. Sketch the image graph after translation of 4 units right and 5 units down. Write the equation in terms of the function j. State the domain and range. All right. This time they didn't give me any critical points to work with. Okay? Notice there are no nice points identified. So if they don't give you any critical points to work with, I'm going to suggest that we actually pick a couple of critical points. So I'm going to pick, I kind of see this one here. And I'm going to pick, yeah, the corners for sure. I guess this one. Okay? Yeah? Now, this is what I'm going to introduce kind of a more formal approach than we did on example 1. And this, moving forward, when we get to the trickier graphs, I'm going to be relying on this formula. And this is what I call mapping. So it's a little weird if you haven't seen it before, but it's kind of foolproof. So I noticed I listed 5 points, right? That's quite a lot of points. So I'm going to list this is how I do it, critical points. Okay, so I'm going to list my critical points right here. And I'm moving from left to right. So my critical points are what? -1, is that -1.5? I guess. -1.5, comma 3. Would you agree? Those are the coordinates of my first point. And then I have what? -1, comma 0. And then I have 0.5, comma 5. 0.5, comma 5. And then 2, comma 0. This is a little overkill, I guess, because probably 2.5, comma 3. But I want to show you the process that I'm going to be using for most of this course. And it's nice to show the process on an easy graph at the beginning. Okay. Now, in lots of our graphs, we don't need 5 critical points. We probably could get by with 3 critical points. So what I'm going to do is, it says, state the image graph after translation of 4 units to the right, okay, and 5 units down. What happens when we shift 4 units right? That's a horizontal shift, right? Correct? What happens to the x values when I shift right? Do they get bigger or smaller when I shift right? They get bigger, right? So, each x value gets 4 units larger. And what about 5 units down? What happens to the y value? Y value gets 5 units smaller. Okay, so when we do a mapping approach, we actually show the arithmetic that we need, but it doesn't actually match the equation, right? So if I take every x value and I add 4, so for every x value I'm going to add 4, and for every y value I'm going to take away 5. Okay? Agreed? Okay, let's do it. Let's just add 4 to the x's. I usually like adding my x's all in a row. So what's -1.5 add 4? 6? I think isn't it 2.5? Let's double check. Someone can double check that, right? 2.5. So 2.5. What's -1 add 4? 3.5. A half added to 4, 4.5, 6, and 6.5, right? I always do my x's first, I don't know why. Okay, now let's take all our y's and subtract 5. 3 minus 5, -2, 0 minus 5, -1, 5 minus 5, 0, 0 minus 5, -5, 3 minus 5, -2. Now, I could have taken each of these points, just so you know, and I could have shifted 4 to the right, it's kind of hard to do, and then 5 down. But, again, I'm going to introduce the mapping approach at the beginning, because once we get into stretches and reflections and we have like 5 different translations, you can't do 5 different, you can't transform your graphs 5 different ones in the same picture, so mapping allows you to do all the changes at once. Okay, so let's see what we got. So now this point becomes 2.5, -2. Okay, so again, I'm moving left to right, so I've got 2.5, -2. That's my first point. Right. 3 comma negative 5, 4.5 comma 0, 6 comma negative 5, and I think I'm off the page, 6.5, which would be about right here, right, negative 2. Okay, now because I listed my critical points left to right, and this is how it panned out left to right again, I can just connect my dots in a left to right fashion. Okay. And the equation of my image graph, okay, well, what's my equation going to be? It was 4 units right, 5 units down. So it's going to be y equals j, 4 units to the right. How do I write that? X minus 4 minus 5. Okay. And I think I have to stop there because we're running out of time. So I'm going to stop there. We're going to continue on. You can all, you've got little notes in your, I'm not going to do the, just so you know, I'm not going to do the conceptual approach for transformations. I'm just going to do the more scientific approach later on. But finish all, the only homework I'm going to give you is finish that 1.1 for homework, okay?